Okay, so we will get to defining NP completeness and try and actually do some proofs today. Several of you would have heard or seen this before, but hopefully it will be something new, and we'll quickly, increase the pace and do some proofs which you have not seen maybe. Okay, so let's recall what we are after. We are trying to show lower bounds basically. Okay, so we have seen lower bounds for small number of problems like sorting, finding median kind of things in very specific kind of models, comparison model, n log n lower bound. We saw some adversary lower bounds and things like that. Now we are just going to scale up and try and argue that certain problems need more than polynomial time. Okay. So, at this point actually we do not have machinery to say that, but we will come up with some evidence to show that some problems cannot be solved in polynomial time. Okay. So, let us recall the definition of P. So, these are problems solvable by an algorithm taking time of polynomial in the input size. Okay, so there are lots of things which need to be defined little more formally because we are developing some sort of a theory. So, what is a problem? Right? We need to formally define this. What does it mean by an algorithm solving the problem, and what is input size? So, this is something I presume you actually, you've seen some lectures on this. So, you're looking at a succinct encoding of the input, okay, and for all practical purposes you can assume it's a binary encoding of your input, okay, and it is very important that it is binary encoding or something related, because the whole thing can have a different meaning. I'll give you some examples where why this encoding is important. Okay, so roughly speaking, we can treat this as some sort of a binary encoding of our input, whatever that is. Okay, it could be a graph, it could be a family of sets, it could be some sequence of numbers, whatever. For some technical reasons, we will be looking at decision problems. Okay, so these are problems for which the answer is yes or no. Okay, so we are going to be confining ourselves to problems for which the answer is yes or no. So, for example, sort a given sequence of numbers is not a decision problem. Okay, so this has a, why are we restricting to decision problems? This, I'll actually tell you a little more formal definition of P, and you will see where it's coming from. And the other thing is, we don't lose too much generality by restricting to decision problems, because optimization or other kind of problems, we will be able to convert it to decision problems most of the time. Right. So, let me just, I don't know whether you went through this about this binary encoding business. So, for example, I have, look at the following problem, given n, is it prime? Right. So, a naive algorithm, what would be a naive algorithm to do this, test this? Given an integer, I want to test whether it's prime. Yeah, so test from 2 to n minus 1. Okay, you can do slightly better. 2 to square root n is also enough, right? Why root n is enough? Because if a number is not a prime, it should have a factor less than or equal to root n, some factor, right? Because if it's not a prime, it has at least two non-trivial factors, and if both are more than root n, the product cannot be less than or equal to n. So so check. So for I going from 2 to square root n, check if I divides n, right? And if any I divides n, then you know it's not a prime, and otherwise you can say it is prime. Now, what is the running time of the algorithm? Well, how many divisions? Okay, first of all, yeah, this is another thing, right? What does time mean, right? What is it? What are we computing? Counting in time? Well, anything which you can, a CPU will do additions, multiplications, comparisons, kinds of operations. So a division is a constant time operation. Then this algorithm takes a square root n time. Now, is it a polynomial algorithm? It's actually even sublinear, right? Yes. So you guys know. So, okay, why is it not polynomial algorithm? Because what is the input size here? The input size. What is the input here for us? The input is n. So if I write it in binary, the input size is log n, not n. Because I am talking about a binary encoding of my input, right? So I want an algorithm which is polynomial in log n, so that I can put this problem in P. Okay, but square root of n, is it polynomial in log n? Square root of n is actually 2 power half log n, right? 2 power log n per. So it's exponential in your input size. Okay. Now you should complain, but whenever we are computing the complexity of a sorting algorithm or finding median or anything, you just said n. You never, looked at binary encoding. Why is this important here? Yes? Okay. So what's the answer? So when I'm talking about sorting algorithm or a graph algorithm, so let's say I have a graph. What is the input size? If I write it as an adjacency matrix, it's like an n square bits. Otherwise, it's like m plus n log n kind of thing. If you write it in terms of bits, right? So for sorting, if I want to sort n numbers, what is the input size? Well, n times or summation log of whatever bits, because if I write each one is, but that's much more than n anyway. So it's n times something, right? So if I have so input size for sorting really would be, summation log of xi. If x1, x2, maybe plus 1 or something, because you need some delimiters. But the important thing is this is more than n, right? So if I call this as capital N, then an n log n algorithm is also capital, right? Because capital N is at least small n. Okay. So we didn't bother about this encoding so much. But two reasons. One, we are not really going to talk about n square n log n here. We are actually going above and talking about polynomial running time. Okay, so this is a big equivalence class in some sense. And secondly, for these kind of problems, the input size is more than n anyway. So using n as an input size is not bad. It's a reasonable approximation. Whereas here, this is not the input. I mean input size. N is the input, but the input size is log n. So one is interested in a polylog, and the reason, okay, why do I care about all this? Let's come to all that. Now, yeah. So what is this big deal about this class P? It is associated with sort of problems with feasible algorithms. Okay, problems which you can really solve in practice for large values of n. Okay, and it is associated with problems which can actually really solve in practice. Why? Because strictly speaking, if you have a problem which takes n power 100 time, it still belongs to P. Would you consider that as a reasonable algorithm? Yes, you may not, but there are very few exceptions of that type. If you look at the class of all problems solvable in polynomial time, typically n square, n cubed, you start with an n power 5 algorithm maybe, and then gradually they are improved to n cubed, n square. In fact, there are people who believe that everything in P as an n log n algorithm or something. Okay, not clear, but so that's one reason where it's feasible, because in practice, whatever we have seen problems solvable in polynomial time are actually solvable in some small polynomial time, where the n power exponent is small. Number two, I mean, why is this associated? I mean, why is this sort of a robust class? Is that a formal definition, if I have to say, I would write this as P languages accepted by a deterministic Turing machine in polynomial time. Here again, polynomial time means time polynomial in the input size. Okay, same thing. So, this actually gives a formal meaning to what a problem is, what solvable mean, and so on. Why? Because you can think of, so what is the language is some subset of 0, 1 star. Think of your encoding, right? So, I mean, typically what do we want to solve? Given a graph, we want to know whether it is Hamiltonian, let's say, right? So, you can think of it as, what is my L would be all encodings of graphs with Hamiltonian cycle, right? So, example would be then what is my Hamiltonianity question, the problem I want to solve, given a graph, is it Hamiltonian? That is what I want to know, right? Which is same as saying, given some encoding of a graph, does it belong to L, right? So, now does it belong to L is the question, and if you can design a deterministic Turing machine which takes this encoding, runs through in time, polynomial time, and at the end it says yes, it's an encoding of a Hamiltonian graph or not, then such problems belong to P. Okay. So, now I have a formal meaning of what a problem means in this kind of a translation of into the language theoretic thing, a language accepted. Now, so far in this course, we did not really specify the model of computation when we said an algorithm. Okay. So, but when I say deterministic Turing machine, you all know or should know what it means, right? It has a tape, it starts from a starting state, it runs through, follows through the transitions and accepts it, right? Now, but if I have to design a Turing machine for sorting or shortest path, Dijkstra shortest path, it's really painful, okay, because you just have to encoding and Turing machine steps are really boring. But the kind of model we have assumed is like a random access model where I can go and access some position of my array in constant time and do these computations in constant time. Now, the reason this P class is robust is also that it is sort of model independent. Okay. Something which you can do in Turing machine can be converted, simulated in a random access machine, but it will slow down a little bit, but not by a polynomial factor. If something is solvable in polynomial time and deterministic Turing machine, you can simulate it in random access machine in polynomial time and vice versa. So, so one reason I said P is robust is because it is associated with problems solvable in practice. The second reason is that it is robust under model of computation, whether you are using a Turing machine or a random access machine, a polynomial problem solvable in polynomial time in this model remains polynomial time solvable in the other model as well. Okay. So, a more formal definition will be something like this. Okay. And there is a third reason, which is that there is certain transitivity, right. There is a you can compose two polynomial time algorithms and you can get another polynomial time. So, you have a problem, right. A takes from some x and produces f of x and it takes polynomial time, and B takes f of x and produces some g of x in polynomial time. You can compose these two and this will still be a polynomial time computation, and this is something which we will use when we talk about reductions and stuff. Okay, good. So, now I mean most of it you have already seen. So, I am just sort of revising what this class is. So, you can put, for example, what are some examples of problems here in P you have seen. Given a graph, is it connected? Given a graph, is it bipartite, right? Given a graph and a pair of vertices S and T, is there a path of length at most 25 from S to T, right? Why is that polynomial time solvable? Given a graph, let us say a weighted graph. Okay. So, I would say is it connected, is it bipartite, no. Does there exist an ST path, length at most 25? Why is this polynomial time solvable? How would you solve it? Apply Dijkstra's, exactly. So, start given this graph S, apply Dijkstra's from S, you know the shortest path from S to every other vertex. So, in particular you know the shortest path from S to T and see whether it is less than 25 or not, you can answer, right. But if I change the problem, I mean, so bipartite is same as two colorable, right. Can you color the vertices with two colors such that every endpoint of every edge gets different colors. If I change it to is it three colorable, we do not have an efficient algorithm yet. If I change this to, is there a path of length at least 25 from S to T, we do not have an efficient algorithm. Okay. Now, I mean, we do not have an efficient algorithm so far to say that you can put it in the class P. Okay. So, which class do they belong to, right? Okay. So, then you are also, I presume, defined a class NP. So, I will come to that. So, given n, is it prime? This algorithm is not a polynomial time algorithm, it is an exponential time algorithm. A polynomial time algorithm for primality was open for quite some time, and it was resolved about 10 years ago by a team of people at IIT Kanpur. This is sort of a very famous result from India in algorithms in the last 15 years or so. Okay. So, what is NP? Is a class of decision problems for which S answer has a polynomial length certificate and a polytime verification algorithm. But in this formal definition, it is so easy for me to define it if you know what it is. Right? NP is a class of problems, languages accepted by a non-deterministic Turing machine in polynomial time. Okay. In fact, the N stands for non-deterministic and not for not polynomial time. Right? So, what is this certificate polynomial time verification algorithm? Well, again, I presume you have seen some examples. Let us say if I ask the question, given n, is it composite? Okay. What would be a easy simple certificate for an S answer? One factor, right? You do not even need all factors. So, you just I give you a number and I ask, is it composite? You say yes, 257 divides the number, and so that is a small certificate because that is like a log of the input size, right, because it is a number much smaller than n. So, the encoding will be linear in the input size. And what would be the verification algorithm is you will take the number and divide by this and check whether it is correct or not, right. So, the division is like a constant time algorithm. Right. So, that put this question in NP. I mean, it is an NP for a different reason as well. We will come to that, but I just give you a certificate, right. So, similarly, given G, is it Hamiltonian? What would be a certificate to say that yes, the graph has a Hamiltonian cycle? The Hamiltonian cycle is a certificate, right. You just give a permutation, you say that go from 1 to 7 to 3 to 5 to 2 to 8 to blah blah blah, and what would be the verification algorithm? It will just go and check the adjacency matrix and verify that your adjacent things are all, they have a 1 there. Right? So, do you see a equivalence between this definition. So you understand what, because you all know what a non-deterministic Turing machine is. So what would be the certificate for an S answer? The accepting path, exactly, right. So non-deterministic Turing machine, which will start from here, and it will have multiple options to go for the same symbol it sees, and if I have one accepting path, because for an S answer there is a polynomial length certificate, this length is polynomial, and that accepting path would be the certificate, and the accepting configuration is the verification algorithm of this Turing machine. Okay. So P is clearly contained in NP, right. If you use this definition, it's pretty obvious to see, because non-deterministic machine is even more powerful than the deterministic machine, and so you can ignore the non-determinism. A deterministic Turing machine itself accepts that language, so it belongs to this. But if you want to use this informal definition, well, if a problem is solvable in polynomial time, I don't need a certificate. I just use the polynomial time algorithm. That would be the certificate, and take its answer, and that would be the verification algorithm. So clearly, anything in P is contained in NP, and I told you that primality has a polynomial time algorithm to this famous result, and so because of that reason also this problem belongs to NP, right, because it actually is in polynomial time solvable. Right? Questions? No. Okay. Fine. So the real big open problem is, are there problems in NP which are not polynomial time solvable, right? Right. So Hamiltonicity is an example where we saw that it is actually in NP, and I told you that there is no polynomial time algorithm so far. Doesn't that prove that this question of is it Hamiltonian belongs to NP but not in P? Yeah. We have not proved that it does not belong to P, right? Because I said this is all about lower bounds and we don't know. We have not been able to show that some problem actually requires more than polynomial time. It's just that we don't know. Our current knowledge, based on current knowledge, we do not have a polynomial time algorithm for this. What other is it also clear that P is contained in, okay, so let me just define, let's define this class co-NP, it's useful anyway. Decision problems for which no answer has a polynomial length certificate and a polytime verification algorithm. So what would be an example? Again, prime, this is a simple example, given a number, is it prime? I don't know how you will easily convince me it is prime, but you can easily convince me that it is not a prime by giving me a factor, right? But actually, even for showing it is prime, there is an NP algorithm. But anyway, so is it clear that P is contained in co-NP? for the same reason, because you have a deterministic Turing machine which will take your input and will answer yes or no. It tells you both, it is not one sided thing, it actually will tell you yes or no. So, you have a no answer also as a polynomial time algorithm. So, it belongs to co-NP. So, P is contained in NP intersection co-NP, and again the reverse direction is open, right. Are there problems which are in NP and co-NP, but not in P? All right. So, we know that there are problems in NP which do not have a polynomial time algorithm now, but we still do not know how to show that they need more time, but there is some evidence to show that these problems actually require more than polynomial time, and that is this notion of NP completeness, right. So, to talk, before we talk about NP completeness, we should talk about reductions, right, where you want to somehow use an algorithm for another problem to solve some other problem, right. This is a very general thing, notion where we want to reduce one problem So, you want to take one problem, encode it into some other problem, use the algorithm for the other problem to solve this, right. This is something we have actually done it. We have done it in several times. I will show you some examples. So, what does this mean? That use algorithm for that is the effect we want. So, for example, I mean I before I define formally what that means, and I have left a box here, I will come to that. But what I want to say is this reduction is something very general. You probably have seen it in your automata course, also in the context of halting problems, right. So, for example, we have reduced bipartite matching reduces to max flow, right, max bipartite matching. Given a bipartite graph, you want to find the maximum set of disjoint edges. And how did we solve it? We said, oh, we set up a flow network, solve the max flow, and from there you get your answer to your matching problem, right. And and how much time did we take? I would say we took m plus n time, where m is number of edges in right. So, we had this bipartite graph. We created a vertex S, created a vertex T, we added all these edges. So, there are at most n such extra edges we added some capacities on these, added some capacities on this. So, that is like an m time, this is n time, and now we say okay, solve the max flow problem. Right. So, we reduced bipartite matching problem to max flow. right. And often this is done so that we can use an algorithm for this pi 2 to solve pi 1. Okay. In the context of NP completeness, we will actually use it to show some sort of a lower bound. Okay, I will be clear why, how, why, and so on. Right. So here is an example. So what this means that we have taken an input of the bipartite matching problem. In m plus n time, we have created an equivalent input to the flow problem. What does equivalent means? That if the flow value is k, then the matching size is k. Okay, that's sort of the equivalence we proved. Okay, so this is what the general definition is, that there exists a function f polynomial time computable function. You are comfortable with Turing machines, think of it as a deterministic Turing machine f, which takes an instance of pi 1 and produces an instance of pi 2 such that what? That I should be able to derive the answer after solving for the instance, right. So if I call this x as the instance of pi 1, it produces an instance f of x of pi 2 such that x is an S instance of, because we are talking about decision problem, where pi 1, pi 2 are decision problems. So in the case of bipartite matching, given a bipartite graph, you might ask the question, is there a matching of size k? That is a decision problem. Then the function f is what we did here. This Turing machine, which adds s and t and adds these edges and adds these capacities. I produce that network such that x has a matching of size k if and only if this network has a flow of value k. Right. So this is about transforming an instance of one problem to an instance of another problem, so that we can use the algorithm for the other problem to solve this problem. Okay, so this is sometimes called Karp reduction, and there is a related notion called Turing reduction, where if I really want this effect, right, I want, so what are we doing here? I've taken an input, produced an input of the other problem, and solve that algorithm. Solve that problem using an algorithm for that problem. Now, I could call the algorithm for the other problem multiple times. Why only once, right? So I might take this, produce that input, solve it, do this several times, because ultimately if my aim is to use algorithm for pi 2 to solve pi 1, I might use this algorithm some polynomially many number of times and solve this. Okay. So think of it as an oracle. Okay. So I just say use algorithm for pi 2 as an oracle to solve pi 1. So can call and in the context of NP completeness, this is basically polynomial time. But you can really, this is where you can refine, play around to define different complexity classes. So if you, for example, care about log space and say that I want the reduction to actually take only logarithmic amount of space. In the context of halting problem, Turing machines, you won't even care about the time. You are happy with some algorithm for this problem, right? You want to show that this problem is unsolvable. Then if I already know some problem which is unsolvable, using this, if I have an algorithm I don't care about whatever time is, then I would have shown. So in that reduction, some algorithm was enough. But in the context of NP completeness, we look at polynomial time algorithm. In some other complexity class, you may look at log space reduction. In fact, now a more popular thing that's happening is that you go to the exponential world. Well, so here it is. For example, here I said bipartite matching I can reduce to max flow in m plus n times. So that means that any improvement to your max flow running time will give me an improvement to bipartite matching. Of course, I may even have a different algorithm for bipartite matching. In fact, indeed we do have, but clearly it follows that. So here we are not talking about polynomial, but we are talking more refined m plus n time kind of thing. Right? So as I said, the current popular thing is you go to the exponential world and we talk about, is it solvable in 2 power square root of n time. Okay, and if this is solvable in 2 power square root of n time, can I solve this in such sub exponential time? Then in the reduction I may allow more than polynomial time, but whatever is required, because what is the overall time, right? So overall time is, what do I have? Time to solve my problem pi 1 in this carp reduction is equal to time for reduction plus time to solve pi 2, right? Because I take my instance pi 1, reduce it, apply the pi 2 algorithm and solve it. So my overall time for pi 1 is this plus this. So now you can demand certain tight running time for this depending on whatever complexity class you are working on. Okay. In the context of NP completeness, everything is just polynomial time. And most of the time we will be working with carp reduction. So let me again give you one more example in this context of tight reduction. So for example, you can say, so one way to read this, so pi 1 poly time reduces to pi 2 is sometimes written like this. You can read it as pi 1 is no harder than pi 2. Right. So, why is this? Because whatever algorithm for pi 2, you can use it to solve pi 1 through this reduction. And maybe a better way to do it as well, you do not even have to go to pi 2. That is why it's no harder, it may be much easier for all you know, because even without going through pi 2, we may be able to solve it, but here is one way. So, whatever time in which you can do pi 2, you can do pi 1 plus whatever the reduction time. Okay. In the polynomial world, that is what this is saying. So, for example, so this is the polynomial time, but let us say here is a matrix multiplication. I want to say this is no harder than matrix inversion. Okay. You have two n by n matrices, you want to look at the time to multiply these two matrices, and I want to argue that this is no harder than the time you need to invert an n by n matrix. Okay. I mean, it is intuitively clear because multiplication seems like an easier problem than inversion, but how do I formally prove this in this? I have to give a reduction, right? Given two matrices which I want to multiply, I want to reduce it to the problem of taking an inverse of a matrix. Okay. Actually, the more interesting thing is the converse is also true, which is more interesting, but I won't do that today, maybe tomorrow. But so the direction is important. So, what do we want? Given two matrices A and B of order n by n, let us say, I want to compute the product A times B. Okay. What I want to tell you is that if I have a black box inversion algorithm, I can use it to solve this, to compute the product, right. So, what sort of transformation I want? I want to take these two matrices, produce some matrix and compute the inverse of that matrix. Somehow the product AB is hiding there and I will be able to pull out from there. That is the goal, right. I want you to think about this goal clearly, because we are going to do this again and again in the NP completeness reductions. So, I am trying to reduce matrix multiplication to matrix inversion. So, the problem I want to solve is multiplication. The problem for which I assume we have an algorithm is inversion. So, somehow I want to use that algorithm to produce the product. Okay. So, here is the magic thing. I compute this. I calculate this matrix D and give it to my inversion algorithm and say compute D inverse. Okay. Turns out D inverse is something where the product AB is sitting somewhere. So, here are the two matrices I want to multiply. I plug it in here into this big 3n by 3n matrix and ask my inversion algorithm. It will produce this, and I pull out this entry and I get my product. Okay, why D inverse is this? You can verify. Just multiply and check that it actually produces identity, right? And so, how much time I have spent? Let's say if m of n is the time to multiply two n by n matrices. How much time I spent? I've spent? Well, I set up this matrix first, so that's like an n square time. Right, this matrix is a 3n by 3n matrix, so that's, and then I apply my inversion algorithm. Let's say I of n is the time to invert an n by n matrix, and this is like right. So, this is time to multiply I make some simple assumptions that I of n is omega n square, right, because if you can invert the matrix even faster than n square, which we do not believe, then the actual time dominated is the reduction time, not the inversion time, right. So, what I want to claim is this is assuming I of n is omega n square these are reasonable assumptions. Yeah, the more interesting thing is actually and surprising is that matrix inversion is no harder than matrix multiplication. That if you have a fast algorithm to multiply two matrices, I can use that as a subroutine plus some reduction time to actually invert a matrix. Okay, so we will see that probably tomorrow. And the point of all of this is that a fast algorithm for one will, as a result of this reduction, will give a fast algorithm for the other. Okay, so you get an idea of reductions. That this is the definition of a reduction. You take an input instance of the first problem, reduce it in polynomial time, because that's what we're going to worry about, to a problem of the second problem, and it's an equivalent instance in the following sense that whatever answer you get here, you'll be able to get back the answer to this problem. Okay, so now when is a problem pi NP complete if first I want it to be an NP, that there is a non-deterministic polynomial time Turing machine that will accept the language in polynomial time, and okay, that this problem is NP complete if it is an NP, and every problem in NP polynomial time reduces to this problem. So, this if it's not an NP, but this condition is true, then we call it an NP hat, right. Okay, this seems like a very strong statement that somehow, so our picture now is that this is the class P and this is the class NP, and we don't know whether there is anything here because this is the, whether NP is contained in P is the open problem. And what we are calling it a problem is NP complete is a problem which is an NP, and every problem in NP reduces to that problem in polynomial time. Okay, so we don't know whether there is such a problem at all. I mean, you probably know already, but you know when it was defined. But what can we say? Here are some interesting immediate conclusions we can say, which is that if pi is NP complete, and if pi is in P, now before that, let's write this. This is just a property of the reduction, right? If pi 1 is polynomial time reducible to pi 2, and if pi 2 is in P, then this is the motivation for which we even define this notion of polynomial time reduction. So, why is this true? Because I want to show pi 1 is in P. So, you take an instance of pi 1, since pi 1 reduces to pi 2 in polynomial time, there is a function f which will convert it into and since pi 2 has a polynomial time algorithm, use the algorithm for pi 2 to solve this, and depending on the answer we know that because of this equivalence, this is yes if and only if this is yes, so you get an answer for x in pi 1. And since the reduction is polynomial time and the pi 2's algorithm is polynomial time, overall you have spent polynomial time, right. If pi is NP complete and is in P, then P equal to NP, then the whole of NP is contained in P. Why? Because we have loaded everything in this definition basically, right. If pi is NP complete, that means that every problem in NP reduces to this in polynomial time. So, if I want to solve a problem in NP, I reduce it to this problem, and if pi has a polynomial time algorithm, you use this polynomial or because of this lemma, you know that that problem belongs to P. So, every problem in NP belongs to P, but we already have seen P is contained in NP, so that these two classes collapse. Also, if pi is NP complete and pi is not in P, then no NP complete problem is in P. because of this lemma, that if some NP complete problem is in P, every NP problem is in P, but you've shown a problem which is not in P, an NP complete problem. So, this suggests that if I want to settle this question whether NP is contained in P, focus yourself on NP complete problems and try and show that, pick any favorite NP complete problem. There are really thousands of them. We will see some today, tomorrow. And you pick any NP complete problem, either try and show that it is not in P, then you would have settled this conjecture in a negative sense that NP is not in P, or you show that it is in polynomial time, then you would have. So, either way, so that is why NP complete problems are important, because they are somehow in some sense hardest of the problems in NP that we do not since most people do not believe this to be true, we expect NP complete problems do not have polynomial time algorithm. Okay. And why most people do not believe this to be true? Because NP is all about verification, P is actually about solving the problem, and intuitively we know that solving the problem is harder than verifying a solution, right? Because solving a problem is your job, verifying the solution is our job, and which is much easier. All right. So, now it's all good to have a powerful definition, but is there some problem at all in which is NP complete? How do you even show that every problem reduces to pi? Okay, so one more thing, let's okay. So, in 1971, when this whole theory started, Cook and Levin showed that this problem of satisfiability is NP complete. So, what is the satisfiability problem? Well, the simplest version of the satisfiability problem is that input has n variables and m clauses, and the question. So, what is a clause? Again, I said simplest because what they showed is a very general version of SAT, but let us look at the CN of SAT. So, a clause CI would be looking like so it's a collection of R's of literals. Okay, these Xi's or Xi bars are called the literals, and its CNF stands for conjunctive normal form. And the question is, does there exist an assignment, a 0-1 assignment to Xi's such that all clauses are simultaneously satisfied? Such a clause is satisfied if x3 is set to 1 or x7 is set to 0 or x2 is set to 1 or x8 is set to 1. So, now you have to set 0 or 1 to each of the variables such that every clause is simultaneously satisfied. Okay. So, is it easy to see that it is an NP? So, let us recall the definition of an NP. You need a polynomial length certificate using which a verifier can verify the S answer in polynomial time. So, what would be a certificate? A satisfying assignment is a certificate that you will say, oh, set x1 to 0, x2 to 1, x3 to 0, x4 to 0 and blah blah blah, and I look at that assignment, charge through each clause, just make sure that every assignment is satisfied. So, you have a n bit witness and a simple linear time verification algorithm which will verify that this assignment is satisfied. So, that makes it a problem in NP. What would be a brute force algorithm to solve this? Try all possible assignments. How many? 2 to the power n assignments are there. For each such assignment, check whether it is satisfied, and that will be a a robust brute force algorithm that takes exponential time. So, what Cook and Levin showed is that any problem in NP can be reduced, which means you can take an instance of that problem, whatever the problem is, and you can reduce to an instance of this SAT such that that is an S instance if and only if this is satisfied. Okay. How would you show that? Well, I mean, we will actually see some version of it, a detailed proof tomorrow. But the formal definition of NP is useful. So, what is the formal definition of NP? That your problem is in NP if there is a non-deterministic Turing machine which takes the input of the string and checks whether it is in the language in polynomial time. Right? So, you just have to, so you are given such a non-deterministic Turing machine, simulate the computation of the non-deterministic Turing machine using a formula. Right. So, how does the Turing machine move from here to that state and follow through that computation and show that you can encode the whole computation into some sort of a formula such that you have an essence, you have an accepting path if and only if there is a satisfying assignment. Okay. So, that is what they showed. Some version of it we will see tomorrow, but I want to start from here and do a couple of reductions. Okay. So, let us okay. So, something like 3 SAT what is a 3 SAT problem? It is basically a SAT problem where each clause has exactly or at most 3 literals. So, this is a restricted version of it, this problem. So, showing it NP completeness is a stronger result, right. Notice that if I showed this NP complete, it will follow that this is NP complete, because this is a more general version. Because if this is poly time solvable, this would be poly time solvable as well, because this is a restricted version of it. So, showing a restricted version is hard, is a stronger result. Okay, that is the point I want to make. Okay, this also we will do tomorrow, but what I want to do today let us do a graph problem. The click problem is NP complete. So, what is a click problem? So, input G and an integer k. does G have a clique on K vertices? Okay, so what is a clique? You all know it's a subset of vertices which are pairwise adjacent. Okay, every pair of this vertices in this subset has an edge. Okay, so typically an interesting question is what is the maximum size clique in the graph? Okay, so now what I want to do is to reduce. So it is an NP is clear, right? Okay, to show something is NP complete, remember there are two things you have to show. Oh, I need to prove another lemma before that. But what are the two things I have to show? That it is an NP, and the second condition is that the formal definition I said every problem in NP reduces to this. Okay. So, before that let me prove a lemma which is more useful. So, pi is NP complete if pi is an NP and pi 1 reduces to pi for some NP complete problem pi 1. And the proof is basically because this is a transitive. Okay, so I'll leave this as an exercise that if pi 1 reduces to pi 2 reduces to pi 3, then pi 1 reduces to pi 3. Right, you can take the composition function and take this instance and reduce to an equivalent instance of pi 3. So, because of this, since pi 1 is already NP complete, every problem in NP polynomial time reduces to pi 1 and pi 1 reduces to pi. So, because of the transitivity, every problem reduces to pi, and you would have satisfied your second condition of the definition of NP completeness. Okay, so to show this is NP complete, first I have to show it is an NP, and I have to reduce from a known NP complete problem to this problem. Okay, the direction is always very important. Reduce from a known NP complete problem to this problem, because what we are trying to show. I mean, what do we mean by its NP complete? Intuitively, we mean that it does not have a polynomial time algorithm, right? That is the conjecture. So, by reducing, so if I want to show that this problem does not have a polynomial time algorithm, I have to show a sort of contrapositive. If it has a polynomial time algorithm, I can use it to solve some other known NP complete problem in polynomial time, which I know it does not exist. Okay, so that's so it's important that you reduce from a known NP complete reduction. So, I would write this very important. Do not reduce your problem to some NP complete problem. It's a standard mistake people do. You take a known NP complete problem and reduce to this, right? Okay. So, I want to show this. So, first thing I have to show that it is an NP. How to show it's an NP? What is the certificate? Subset of K vertices, right? Because that's the question. A subset of K vertices would be a certificate, and the verification algorithm will just check that there is an edge between every pair of them. Okay, so put this in a box. So, S contained in V is a certificate, and the verification algorithm checks cardinality is equal to K and right? At least one thing I want to write formally so that you know what to write when in your assignments, right? I don't want you to say it's NP, easy to check, right? Usually it's easy, but please do write the formal definitions. Okay, so now I want to reduce from a known NP-complete problem to this problem. Well, so far the known NP-complete problems for me are these two problems. So this is always a hard thing, right? Where do I start? Which problem do I start from? Because you have choices, hundreds of choices. But in our case, we have shown only these two problems. So SAT is usually something quick to check, start from. Okay. So I want to say SAT, polynomial, or let's say 3 SAT, doesn't matter really to this click problem. Right? I want to take a known NP-complete problem, reduce in polynomial time to this problem. Okay. What does that mean? I take an instance of 3 SAT. So this instance has some variables, clauses, and I have a formula which is, and what is my goal? I want to construct a graph G, some integer k, with what property I want? I want f is satisfiable right. So coming up with the problem, coming up with the reduction are not always easy, but at least I want you to remember this template, that known NP-complete problem, I want to reduce to this, and what does that mean? An arbitrary instance of this NP-complete problem, in this case variables, clauses, formulas. From here, I want to construct a graph and an integer such that this is satisfiable if and only if G has a k click. Now let's see how we would go about doing this, right? Because it's sort of like different kind of problems. This is a graph problem, this is a problem in logic, and that's what makes this whole NP completeness theory interesting, right? So it connects problems of different nature. Okay, so how do I view this, right? So here is the connection. What I am looking for is some assignment to the exercise that will simultaneously satisfy all the clauses. And here what I am looking for is a subset of vertices that are simultaneously mutually pairwise adjacent. Okay. So somehow a satisfying, so if you have a satisfying assignment, C1 is satisfied by somebody, C2 is satisfied by somebody, C3 is satisfied by somebody, and somebody is satisfying Cm. I want to collect these guys and somehow argue that they form a clique here. Okay. So I am just sort of talking about how I would construct the graph. So what is my graph, right? So the graph is, so remember, you are given this variables and clauses, I want to construct a graph. So let's do an example, right? So my C1 or my formula may be something like this. My graph is going to contain these vertices. So it is, if you like, it's like an M-partite graph. If M is the number of clauses, I am going to have a set of vertices for each clause, set of 3 vertices, because there are 3 SAT instances, right. So dot dot dot, I will have this. And what is my intuition? I want to say that if this is satisfiable, whoever is satisfying C1, whoever is satisfying C2 and Cm, I want to pick them all and get a click out of them. Okay. So, this suggests what should be my K, M, right. Remember, this is your choice. You have to produce this from here. That is your polynomial time deterministic Turing machine, or your function f, which is sort of transforming an instance from here to here. So, I want to construct a graph G such that this is satisfiable if and only if that has an M click. Okay. Well, so again a starting idea would be, I am going to draw all possible edges, complete M-partite graph. Okay. So, there is M set of vertices. So, the same variable is repeated multiple times, but that is okay, I will have multiple copies of that vertex, and I have a complete M-partite graph. Okay. Now, if f is satisfiable, there is some assignment that satisfies f, right. I take the corresponding, suppose x3 satisfies this, x5 satisfies this, and maybe x3 satisfies here, then I will have a 3 click here, because I made complete M-partite here. Okay. But I will have an M click all the time, even if it is not satisfiable, because if you see, I have a complete M-partite graph, pick one from here, one from here, one from here, any of combination of them. So, what do I want? I want satisfying assignments alone to get mapped to an M click. Okay. So, what sort of M clicks will not correspond to a satisfying assignment? Okay. So, remember, an M click will always pick one from each, because I have not added any edges inside a set. So, an M click will pick something from here, something from here, something from here, something from here. Why do not I just go and set the corresponding variables 1 and I will satisfy that clause? Where will I go wrong? If a variable and a negation are here, suppose I end up picking x3 here, and I might pick x3 bar here for my M click, then the assignment will say put x3 to 1 here and x3 bar to 1 here. I know I can't do it. Okay. So, I want to now come back and change my graph. This is another important, very important thing. When you do this construction, you only know the instance. A common mistake people do is to take a satisfying assignment and then they will do the construction. No, you do not have that luxury. You have an instance which you are in polynomial time, you are converting into an instance here, right. You can't look at a satisfying assignment and then decide on your graph. Okay. So, now I want to come back in this instance, instead of making it complete M-partite, because that is going to throw me some spurious clicks which do not correspond to satisfying assignment. I do not want to add certain edges. Which edges do I not want to add? If you have an xi in one part, an xi bar in another, I will not add an edge, because that click will complicate things for me to get a reverse direction. So, so G has M set of vertices, one for each clause, and xy is an edge of G if x and y are in different sets and the literal is not negation of the other. In this case, there exists a satisfying assignment xi equal to some vi, right? Vi is 1 or 0. For f implies the corresponding vi's form an m-click, because if you have a satisfying assignment, I pick the variable here which satisfies this, and I know that it's not possible that one is the negation of the other because these are all set to 1. So, because of my construction, they will form an m-click, and conversely, if you have an m-click here, okay, let me just write. The click should pick exactly one vertex from each set. Why? Because you cannot pick 2 from each set because it won't be a click. Again, because of my construction, each set is an independent set, so it cannot pick more than 1. It cannot pick less than 1 because it's an m-click. So, it has to pick exactly 1 from each set. Now, set the corresponding variables appropriately. Meaning, if you pick x3 from here, set it to 1. If you pick x2 bar from here, set x2 to 0, and so on. That would form a satisfying assignment. So, f is satisfiable So, we have successfully shown this, that given an instance of 3-sat, actually we did not really use 3-sat, any CNF sat is good enough. I have produced a graph such that, and an integer m, such that G has an m-click if and only if this is satisfiable. So, I have shown that this reduces to this. This is already known to be NP complete. We have already also shown it to be in NP. So, that makes this problem NP complete. Okay. Let me leave with some exercises and we can continue tomorrow. Independent set is NP complete. Vertex cover So, independent set is you want to find a subset of vertices which are mutually pairwise non-adjacent, and vertex cover is a set of vertices such that they cover all edges. For every edge, at least one endpoint is in this subset. And by this, what I mean is, given a graph and an integer k, the question is, the decision question is there an independent set of size k? Is there a vertex cover of size k? And try and see how you would show them NP complete. At least so far, your choices are limited where to start from. So, it should be easy. It will get harder because you will have a bigger set of choices as we move on. Okay.